Hello everyone. So this is a problem from AMC 12 and we solved this problem using a different method previously. Today we will talk about method 2. So it's not a problem if you have not seen the previous video. This will be a completely fresh retake on the same problem. So we start with a square ABCD, A, B, C and D. The side length of the square is given to be 30. So this is 30. And we choose a point P inside this square ABCD such that PA, PB is given to us. PA is equal to 12, PB is equal to 26. We join the remaining 2 points with P, so PD and PC. And then we mark the centroids of each of these triangles. So if you don't know what is a centroid, it's just the intersection point of the medians of a triangle. So centroid is the intersection point of medians of a triangle. So if we take this particular triangle, just for an example, APD, and if we mark the medians of it, so median means you join a vertex to the midpoint of the opposite side. So this is the vertex A and this is the opposite side. This is the vertex A, this is the opposite side. Okay, so similarly what you do is you mark D and the midpoint of the opposite side to D. So this is the midpoint of AP. And finally, you take P and you mark the midpoint of the opposite side to P. So this will be the median of AD. It's a theorem in geometry that all of these medians will pass through a single point. So let's call that point R. I'll change the color, use black. So R, S, T, U. Our goal is to find out the area of RSTU. Now in the previous discussion, we found it using a different strategy, using synthetic geometry. In this particular video, we will use a bit of complex numbers to solve this problem. In particular, we will show that RT is perpendicular to SU. So this is our goal. Our main goal, just to keep that in mind, our main goal is to find out the area of RSTU. That's our main goal. Our temporary goal is to show that RT is perpendicular to SU, and using that we want to find out the area of RSTU. Okay. So what is the idea? The idea is actually quite simple, that since R is the centroid of APD, if we assign complex coordinates to A, P and D, it's very simple to find out R. So suppose the complex coordinate of A is A, D is D, P is P. When I say complex coordinates, it's a number like 2, 3 maybe, or 2 plus 3i, whatever the coordinate of A is. Okay. So what would be the coordinate of R then? Well, the coordinate of R will be simply A plus P plus D by 3. This is the complex coordinate of R. If the coordinate of A is capital A, coordinate of P is capital P, coordinate of D is capital D. It's the way we can denote these particular coordinates. Then the coordinate of the centroid is A plus P plus D by 3. This is also a common knowledge tool in coordinate geometry or in complex numbers. Okay, similarly, the coordinate of R is P, coordinate of T is B plus C plus P by 3. This is T. Okay, so now we have to do a little bit of work. We will be focusing on RT, this particular segment. So instead of that, it's a common strategy and you can use it less elsewhere as well. Find out R minus T. And I'll tell you why I am interested in R minus T. I will compare it with A minus B and D minus C. Okay, I can either compute R minus T or T minus R. It doesn't really matter. I'll show you why. So I'll change the background. Why do I want R minus T? The reason is this, that suppose this point is R and this point is T, and we are interested in this vector RT, then one standard technique is to bring this vector to the origin. So basically we do it by completing the parallelogram. You think of it as floating this particular vector to the origin. So R floats to O, the point O. It's a translation by negative R. That's how you should think about it. So R goes to 0, 0. So basically R minus R, because the translation is by negative R. Only if you subtract R from R, you will get to 0. So R goes to the origin, and all the points actually go to translated by minus R. So in particular, T is translated by minus R, T minus R. So T minus R is this vector based at the origin and parallel to the original RT vector. Okay, R minus T will be the opposite one. If you want R minus T, you basically would do this. You would translate T to the origin, and then R will be pulled here, and this will simply be R minus T. So you can work with any one of them, T minus R or R minus T. It doesn't really matter. Okay. So why this is important? Because R minus T has the same length, or T minus R has the same length and direction as the original segment, as the original arrow. So as far as the length and the direction is concerned, we can as well focus on T minus R instead of worrying about this particular RT segment. And since it's based at origin, a lot of things becomes much simpler. Okay, so let's go back to this picture now. Let's find out T minus R. So T minus R is simply B plus C plus P by 3 minus A plus P plus D by 3. So what do we have here? We have the P and P cancels. So we have B minus A by 3 plus C minus D by 3. Okay, so notice one thing, that BA and DC they are parallel straight lines with exactly the same length. So B minus A and C minus D, they will be exactly the same vector. Whatever the value of B minus A is, whatever B minus A is, let's call it X. So this X vector, C minus D will also be the X vector. So this has simply become 2 by 3 of the X vector. Okay. Now, I told you this will be a little bit more complicated than the synthetic geometry one, but it's much more simpler in this way. Why? Because notice that this tells us two things. The first thing that it tells us is that the length of t minus r, the length of t minus r is 2/3 of the length of this side. So let me write that. Length of t minus r is 2/3 of the length of x, and the length of x is 30 degree. Length of x is just this side length, this vector from A to B. So the length of x is 30, so this is simply 2 by 3 of 30, which is just 20. See how fast we got that the length of RT is 20. And the second thing we have is that it's a multiple of this. Okay, maybe I can write it like this. It's a multiple of this x vector, which basically means it's parallel to this x vector. So RT is parallel to this x vector and its length is 20. So RT is parallel to AB and BC. Similarly, we can show that SU is also 20 and it's parallel to AD and BC. So what are the informations that we have? We know that SU, okay, maybe I can use this one. SU is 20 and parallel to the vertical side. RT is 20 and parallel to the horizontal side. And this is the quadrilateral RSTU. We know that these two are equal and perpendicular to each other. Now, can you tell me what is the area of this quadrilateral now? It's very simple from this point. So I think you can do this. This is the second method of doing this problem using the method of vectors and complex numbers. You see how powerful vectors and complex numbers are in geometry. I'll see you in the next one. Keep on doing great mathematics.